Hello, and welcome back to AI for Retail Executives. This lecture, we are striving for a general theory for retail. Now, by no means is this the end-all be-all. This is just to highlight how complex retail actually is. You have many things in your control. You have price, you control the labor, you control the layout of your stores. There's a lot of intermingling variables that matter a ton. And thinking about any one in particular in isolation and optimizing for that one in particular will, by definition, mean that you are being suboptimal in some other area of your business. And so let's jump into it. We have an example that is to highlight how complex retail really is that I think is I've thought about a ton, and we call it the 2 SKU grocery store. And so let's get into it. So let's say I have a grocery store that has exactly 2 SKUs. And so let's say that we're trying to determine I can have these facings here. This is my whole grocery store right here. And I can make them Pepsi, 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 Pepsi. Or I can have it be Pepsi, Coke, 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 Coke. Or I can have it be Coke, 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 or anywhere in between. It's completely up to me. But I can't add any space, and I want to find the combination of Pepsi and Coke that is going to maximize my EBITDA. And so we'll set this up in true optimization framework using the standard form, as we talked about it before, is you want to maximize EBITDA. You can use free cash flow. It's fun. Same thing for this example. And we're going to maximize, and the variable that we're going to introduce is shelf capacity. Let's say that how much shelf capacity I put for SKU 1 and for 2. And so we're going to say shelf capacity for SKU 1 and shelf capacity for SKU 2. And those are the 2 things that I'm trying to deal with. And the sum of shelf capacity 1 and sum of shelf capacity 2 can't be bigger than my store, right? So that's going to be my constraint. Subject to a constraint 1, which is that shelf capacity 1 plus shelf capacity 2 has to equal the size of my store. Size of store. Okay, easy enough. So let's break this out. So let's say and there's a couple of different ways that we can use AI to solve this. And so we have an objective function. AI should be able to solve this, no problem, right? And that way we don't have to worry if we're not optimal. And so let's see how we would solve this. So the first way we can treat it is an RL problem, reinforcement learning. Well, we have our input, shelf capacity, and then we have some black box. We don't know how it works. We don't pretend to know. We don't care. And it's going to output some EBITDA value. EBITDA. So we put in shelf capacity 1, we get EBITDA 1. We put in shelf capacity 2, we get EBITDA 2. And then we keep learning to try to maximize EBITDA and making changes to optimize it. This won't work that well. It would just take a long time. Remember, our goal in machine learning is to make the problem more and more tractable, meaning we make it more and more convex or linear if we can. That way we can actually solve the problem optimally. So that's method 1. So we'll call this here method 1. RL method. RL way. So we can play the game of retail millions and millions of times. Method 2 is to try to get a little bit more clever. Can we break down, and we'll call this the call it the convex optimization approach. And we'll see if it's even, we'll need to use some machine learning models. Let's find out. So let's break out EBITDA. This equals, we have revenue minus COGS equals gross profit. We have, we'll scroll down here. Then we have labor. We'll call it SG&A. And we have the carrying cost of our inventory, let's say. Cost of carry of our inventory. So what is gross profit equal to? So if we this would be the sum of all of our SKUs times the sum of all of our SKUs of the movement, so the price minus the COGS of that SKU times the movement, how much we actually sell of that SKU, right? So nothing crazy here, but you're going to find out, well, how does that relate to shelf capacity? And so we have to define a few different assumptions down here. So let's do that real quick. So the assumptions that we have are: 1, there has to be some idea of demand. So we have to know, let's say that we make an assumption on the demand of Pepsi, the demand of Coke, some idea of substitution rate from Coke to Pepsi, some idea of substitution from Pepsi to Coke, and let's see what else here. The price, obviously, we need to know what the price, we're going to treat that as an input, and the cost of each SKU. So let's do this for Coke and Pepsi. The price of Pepsi, cost of Pepsi, COGS, how much we have to actually pay Pepsi for the SKU, price of Coke, the cost of Coke. Let's see what else needs to be defined for us. A few other really important ones here. So the weighted average cost of capital. We can stay in stock if we just get all the inventory in the world, but that money's not free, and so we would have to pay that weighted average cost of capital. Typically, that's 3-4% for a big retailer. And the cost per replen. And so the cost, how much does it cost us to replen a single SKU? And so typically, if we're paying our associates at $20 an hour and we can replen at 20 times an hour, it costs us, let's say $1. So that's that example. And then finally, I'm just treating this as epsilon, is like the additional overhead of how much it costs to stay in stock or to add an additional SKU into your entire supply chain. And so there's an administrative overhead. Let's say it costs us $1 per day to do that. Something like that. Cool. All right. So we've made these assumptions here, and so now we can actually break this thing out further. So if we break out our movement, well, how much do we sell? So the movement of Coke should equal to let's make sure I get this math right here. The minimum of my shelf capacity for Coke and the demand for Coke. And so the shelf capacity, so let's just explain this. So if I have shelf capacity of 0 for Coke, the demand is 100, I sell 0. I don't have any Coke, so I sold none. If I have shelf allocation of 100 and my demand is 0, it's 0. No one wants it. If my shelf capacity is 100 for Coke and I have demand of Coke for 100, but I have Pepsi customers coming in as well, then, and some of those are going to substitute into Coke customers because they don't have Pepsi. And so you have to account for that term as well. And so the demand for Coke is the original demand for Coke plus my substitution rate. So what percent of Pepsi customers are going to substitute from Pepsi to Coke into Coke, and the how much demand there was for Pepsi originally, or unmet demand, let's say that, which would be, in this example, the maximum can't be negative, so maximum of 0 and the demand of Pepsi minus the shelf capacity for Pepsi. And so that's the original demand for Coke plus the substitution rate to go from Pepsi to Coke times the max of 0 and demand for Pepsi minus shelf capacity of Pepsi. And so if shelf capacity is 0, there's demand of 100, and out of the 100 customers that walk in and they want Pepsi, let's say 20% will sub out to Coke, and so I get 20 more sales of Coke plus the original demand for Coke there. So that's my demand for Coke. And so that's, we're going to generalize this here. And so what you're going to end up with is your revenue minus COGS is going to equal the sum over all your SKUs. And we're going to pretend that this is just like one day of this grocery store. The sum of all my SKUs equals the price of that SKU minus the cost of that SKU times the movement. And we define the movement to be the min of shelf capacity for that SKU and the demand of that SKU. And so the demand, we said, is the original demand, ds. We're going to call this 1 just to make it easier, because we're going to have a second SKU, plus the sum over S2 of the substitution rate from S2 to S1, and the max of 0 of demand of S2 minus shelf capacity S2. Okay, so that's term number 1. Okay. We jump back here. Now we have to define SG&A and the cost of labor. So this SG&A, how much does it cost us to stay in stock on a SKU? It's not free. So let's jump in here and say my SG&A is going to equal to the sum of all my SKUs, how I have to stay in stock in each SKU, and the cost per replen times my number of replens. For that SKU, S. And the number of replens, this is equal to my movement, we already defined that up there, divided by of that SKU, divided by my shelf capacity of S. And so if I have, and if it's negative, 0 divided by 0 is 0. Let's just say that. So if my movement is 100, if I'm going to sell 100 and my shelf only holds 10, then I need to replen 10 times. If my movement is 10 and my shelf capacity holds 100, And so then I never really have to replan, at least that day. Every 10th day, I'm going to have to replan. And so we'll average it out over 10 days to be 1/10. So that's it. And then finally, my cost of carry. So inventory is not free on your books. Your CFO, I'm sure, knows that. It's going to be very expensive to carry more inventory on your balance sheet, even though that may be a good idea. It just may be, depending on the weighted average cost of capital. And so this one is pretty simple. This is just the sum over all my SKUs. This is equal to the weighted average cost of capital times the sum over all my SKUs, the cost of each SKU, times the amount that I have of that SKU, which right now shelf capacity, equals to the shelf capacity of that SKU. Yes. So there's no back stock, there's no top stock in this naive example, but yeah. So there you go. This is basically, we have this term here, we have this term here, and we have this long term here. And that's basically it. And so what we need to do now is put that into our optimization framework and decide, is that non-convex, is that convex? Can we solve shelf capacity of 1, shelf capacity 2 optimally, and find what our goal is to find SC1 star, SC2 star. That's what we're trying to find here. Well, so I put this into a little example here. So I made these assumptions. I said that, okay, the demand is of Pepsi per day is 55. The demand for Coke is 30. The price that we're going to charge is $3. The price that we're going to charge for Coke is $3.25. The cost to us is $1. The cost of Coke is $1.10. Weighted average cost of capital is 3%. The cost per replan is $1. $20 per hour divided by 20 replens per hour. And then the overhead of one additional SKU in my store is, let's say, 10 cents. And then my sub rate from Coke to Pepsi, if I were a Pepsi customer, would I switch from Coke to Pepsi? Or Coke customer, would I switch from Coke to Pepsi? Let's say 25% of Coke customers will switch to Pepsi. And let's say that 80% of Pepsi customers will switch to Coke. Let's say one's much more brand loyal than the other. And then you get this really interesting property. So we'll look at a distribution. Let's say we have 100% Coke in this example, 0% Pepsi. And that gives us free cash flow, I'm using it as a proxy for EBITDA, fine, of $157 a day. And let's say that, and this is how it breaks down. And you can go in here and play around with this. This is provided as some of the material. And let's say that I keep moving that up to higher and higher percentage of Pepsi and less percentage of Coke. Again, I have a fixed size store. And you're going to find out that if we did 100% Coke, 100% Pepsi, that gives us $124. So, and the delta between the lowest and the optimal, it went from $124 to the optimal is 65% split. So we want 65% Coke and 35% Pepsi, and that gives us $172 in free cash flow a day. And so it's a meaningful delta, and these are all, in my opinion, very real numbers that would happen in a convenience store. And you can find out that using our optimization, we can actually find an optimal solution here. Now, it's intractable to try to do this for all SKUs. The interesting thing here is showing that, given a strategy that this is the size of my store, this is the types of SKUs I want in my mix, once I know all those things, I can input that and find the optimal tactics, which is shelf capacity, the amount of labor that I need to have in my store, and the amount that I should be forecasting. And so if you wanted to generalize this to 30,000 SKUs, it would be what they call in machine learning intractable. So this is where you would need a convex optimization framework to play these to find the optimal shelf capacity of all my SKUs and the optimal amount of forecasting, and so or inventory to order. Now, if I just change one of these variables, let's say demand changes very frequently. So if I change this to 50 and I change this to, let's say more people, want Coke now, it dramatically changes. And that's 45%. So now it was 65%, now it's 45%. If my COGS go up to $1.20, how does that change? That changes quite a bit. If this goes down to 60 cents, that changes again. And let's say that my weighted average cost of capital increases. That's going to change again. And let's say that labor costs increase. Well, that changes everything. Let's say that this goes to $10. That changes a lot. Let's say my overhead is now $45. Well, now it changes a ton. Now it's actually cost negative to include, to be all Pepsi. So I'm not making money there. And so your optimal is still the 45% split, but it's more severe. Let's say that switching changes. And so let's say that that's 0.5 or say 0.9. This is 0.1. Then it changes again. So this shows the complexity of retail. And this is just a naive little example where we just have Coke and Pepsi. Okay, cool. Well, that's all I wanted to show. This is our toy example. Would love your input on it. And think about this. Like, try to think about how frequently these inputs change and how infrequently your planogram changes, how infrequently your forecasting changes, how infrequent, the cost per replenishment changes based on your SOP. You can increase your pick velocity, in certain SKUs. And think about the minimum wage increases. How does that change? It's hard to believe, but it will. It change the optimal strategy for your planograms. The cost of labor, that's an input into this. The stock market and the Federal Reserve rate. When the cost of money increases, it should change your planograms and your ordering. It's all interrelated. Okay, well, that's all for this lecture. We'll see you in the next one. Thank you.